Do you know what our planet looks like on the inside? You've probably seen pictures like this one showing the layers inside the Earth. You've got the crust on the outside, the mantle underneath, and then the outer and inner core. Scientists tell us that the mantle is made of solid rock, while the outer core is liquid. The inner core, they say, is solid again. But how do scientists know all that? Nobody's ever dug down into the Earth's inner layers. How can we possibly claim to know what's down there, or if the layers are in solid or liquid form? Well, believe it or not, we do have legitimate evidence for the state of the Earth's inner layers. To understand it all, we'll have to learn a bit more about waves. When you picture a wave in your mind, you probably envision a transverse wave. It kind of looks like a squiggly line with peaks and valleys, which we call crests and troughs. In a transverse wave, the particles of the medium move perpendicular to the wave's direction of travel. Imagine a line of people all holding hands. If the first person on the left jumped up and down, they would pull on the hand of the next person in line, causing them to jump up and down too. This would continue on down the line to the right until everyone had jumped up and down. The people are like the particles in a medium. They move up and down while the wave moves from left to right. This type of wave gets its name from the fact that the particles move in a direction transverse to the direction of the wave. Transverse waves can be mechanical or electromagnetic in nature. A mechanical wave is a disturbance that travels through a medium, such as a vibrating string. In contrast, electromagnetic waves, such as light or radio waves, don't need a medium and can travel through empty space. While all electromagnetic waves are transverse, mechanical waves can be transverse or longitudinal, which brings us to our next type of wave. In a longitudinal wave, the particles of the medium move parallel to the wave's direction of travel. Let's go back to our line of people to see what this would look like. In this scenario, instead of the person on the left jumping up and down, they bump into the person next to them. Now this next person, being knocked off balance, will bump into the person beside them, and so on down the line. As each person regains their balance, they return back to the place where they were standing before being so rudely disturbed. As we can see, the wave traveled from left to right again, but this time, the motion of the people was also left and right. To help us remember this relationship, we can think about how the motion of the particles is along the longitudinal wave. While transverse waves have crests and troughs, longitudinal waves have compressions and rarefactions. A compression is where the density of the wave medium is highest. In our line of people, this was where folks were actually bumping into each other. A rarefaction is where the density of the wave medium is lowest. In our line, this occurred just after the compression where the people were spread out, trying to regain their balance. Just like the wavelength of a transverse wave is the distance from crest to crest, or trough to trough, the wavelength of a longitudinal wave is the distance between compressions or between rarefactions. When it comes to mechanical waves, transverse and longitudinal waves are not equal. While a longitudinal wave can travel through solids, liquids, and gases, transverse waves can only travel through solids. To understand why this is, let's go back to our line of people who were jumping up and down. When we saw them before, everyone was holding hands, which allowed one person to pull on the next. This bond between people is like a solid object, where the particles are strongly connected to each other. Now imagine that the people stopped holding hands and the first person jumped. Nothing happens. Without a strong connection, one person can't get the others to jump. This is like a liquid or gas where the particles are not strongly connected to each other. On the other hand, a longitudinal wave can be transmitted whether the people or particles are strongly joined or not. All they have to do is bump into each other to move the wave along. Now you may be wondering about all those water waves you've seen at the beach. Those sure do look like transverse waves, and in some respect they are. But the waves you're seeing are actually a special combination of transverse and longitudinal waves, called surface waves. A purely transverse wave cannot travel through liquid. The inability of transverse waves to travel through liquids played an important role in discovering the layered composition of the Earth. Anytime an earthquake occurs, it sends out seismic waves in the form of longitudinal P waves and transverse S waves. As instruments became more sensitive, geologists learned that the seismic waves from a single earthquake could be measured at locations all over the world. However, they also learned that only the longitudinal P waves were arriving at the opposite side of the Earth. Something was blocking the transverse S waves. Knowing that transverse waves could only travel through solid material, scientists were led to the conclusion that the outer core of the Earth was actually a liquid. Waves can be divided into two major groups, transverse waves and longitudinal waves. In a transverse wave, the particles of the medium move perpendicular to the wave's direction of travel. Transverse waves are characterized by peaks and valleys, called crests and troughs. In a longitudinal wave, the particles of the medium move parallel to the wave's direction of travel. This type of wave is characterized by areas of high and low densities in the medium, called compressions and rarefactions. While a longitudinal wave can travel through solids, liquids, and gases, transverse waves can only travel through solids.